it's my pleasure to welcome Dr. Artur Schweidtmann. He's an assistant professor in the chemical engineering department at Delft University of Technology, or TU Delft, where he leads the Process Intelligence Research Group. His research focuses on integrating AI, machine learning, and process systems engineering to advance chemical engineering applications. This includes developing algorithms for process optimization, surrogate modeling, and molecular property prediction. Dr. Schweidtmann earned his Master's of Science in Chemical Engineering from Aachen University in 2017 and PhD from the same institution in 2021. During his studies, he spent the 2013-2014 academic year at Carnegie Mellon University as a visiting student and conducted his master's thesis at the University of Cambridge. So with that, I'll go ahead and turn it over to Dr. Schweidtmann. Welcome.
Perfect. Yeah. Thanks a lot, John, for your kind words and introduction. Thanks for the invitation and for organizing the webinar. So thanks a lot for joining. Today, I'd like to give you a webinar on large language models for chemical engineering. And I will start with the obvious, being that generative AI, and in particular, large language models, have been rapidly developed over the past few years. And have been adopted quite broadly in public, right? And this is probably why all of you are here, because everyone heard about ChatGPT, everyone has used it already. And ChatGPT being just one of the examples of large language models being accessible through web APIs to the public. And I think all of you have experienced what these models can do already with text. So you can communicate with chatbots like ChatGPT quite fluently. You can ask questions, general knowledge questions, but also more specific in your domain in chemistry and chemical engineering about textbook knowledge. And these models perform already at an impressive performance. Of course, they're not perfect. Of course, there are still errors, there's hallucinations. But the rate that these models improve leaves us stunning, and also thinking about how can we use these in actual work, right, in engineering. I think that's the question that I want to discuss with you today. Are these models any useful for chemical engineering, in particular for chemical process development, process engineering? And how would it look like? How would it feel if we would have them in our domain? And what does it take to further develop it? And of course, these models don't work only on text or natural language. They also work on other modalities, we say. So we know there's images that can be generated by models like ChatGPT. There's models that can generate videos, or more close to our domain, there exist generative models that can generate molecules, for example, molecular structures. And these have been or are currently developed in, for example, pharma companies, in research groups, and so on. But I'd like to focus a bit more on the engineering aspect of chemical engineering, the process engineering aspect. And here we don't have much literature. We don't have a lot of tools available yet. So what I want to discuss with you is how would it feel like to have Gen AI or large language models in our domain, and what does it take to develop them, and would they be any useful? Is it feasible? Is there a business case for that? Is this the future, or is it just another random idea that turns out not to be making it to the practice? And before I go into the engineering world, I'd like to talk about large language models and just give a few examples of different use cases where these kind of models are used. And the first one being GitHub Copilot. So in GitHub Copilot, we have large language models. Usually these are transformer architectures trained not on English language, but on computer language, on code. So this can be Python code, for example. So this is a model that is basically auto-completing your code while you develop it. So for example, if you were to implement a function in a programming language like Python with a specific purpose, you could just write a small comment saying like, now I write a function that counts from 1 to 10. And there's a fair chance that GitHub Copilot would pick this up and directly give you implementation or suggest an implementation for this function. And it's believed that these kind of models will really change the way we develop software. So it's believed that large language models like GitHub Copilot here will decrease software development cost by a factor of around 50% in the future and accelerate developments. Of course, there's not only sunshine, there's also a lot of discussions about the use of Gen AI or large language models in these fields. For example, in the context of education. So if all the developers in the world are going to use these models, we may need less junior developers because the simple tasks are taken up by the model. But how are we going to educate our senior developers in the future if there are no junior developers anymore, for example? Or do we still need to teach that? And we have these discussions also in university, of course, and also in different fields. So a lot of discussions about the use of data, like what are these models trained on? How can we use them? Is it okay? Is there a leakage of my intellectual property here? Are we, or should we reward the people writing open source code when we develop these models? So a lot of discussions, but what I want to focus on is a bit the core of the technology here, which is large language models enabling a transformation of this development of software code. And have another example of this transformative character of large language models in specific domains, which is, for example, in machine translation. So here are models like DeepL or software packages like DeepL or Google Translate. You can also translate stuff with ChatGPT nowadays. I just ask it, hey, can you translate this from language 1 to language 2? And the model will do a fairly good job, likely. Again, the quality might not be perfect, but they're reasonably accurate. And in particular in languages that are maybe not easily accessible for all of us. So for example, if I were to give you a book and ask you, hey, can you translate this from Chinese to Japanese? You would likely struggle with this task. But with the help of large language models or translation engines that are more often based on similar architectures, like neural networks with transformer architectures nowadays, you can do these tasks in a matter of minutes, maybe hours for a bigger book, right? And with very low cost compared to the manual translation with a translator, right? And this is where we see this disruptive nature of large language models developed for specific applications here. So they really changed the whole translator business, right? Another example is Grammarly, which is a software for finding and correcting errors of language. Again, it's not only large language models, it's a combination of different models. And may not be as transformative as the other example, but still, if you're a book editor and I give you a book to edit, to correct, maybe with 2,000 pages, 3,000 pages, these kind of tasks are significantly easier now, given tools like Grammarly. So it really reduces the number of errors you make in such a writing. So what we see is in other domains, there can be a transformative action resulting from the use of large language models or development of like or similar Gen AI applications. But I don't want to talk too much about other domains. I want to talk about the process engineering domain, the chemical engineering. And here, what I want to emphasize is that most of the applications you see, the successful applications of large language models, are based on language, on natural language. So here on the left-hand side, we have code. We have, English text maybe. However, in our domain, we don't work that much with language only. We have a lot of the engineering knowledge encoded in different kind of data formats. So we communicate, for example, the relevant topology information of a chemical process in diagrams, engineering diagrams like process flow diagrams, block flow diagrams, piping and instrumentation diagrams. So a lot of the engineering work is around these diagrams. And today I will focus on these diagrams, large language models or Gen AI more generally in these diagrams. However, if you happen to be, an organic chemist, just think about your own data modality, your own data. Or if you're coming here listening in and you're in operations, think about time series data, right? So just take the engineering diagrams as one example. The key point is really that I don't want to focus only on the modality text. So if you want to develop large language models or Gen AI in your domain, within chemical engineering or even outside, don't limit yourself to text. I think that's my main message, first of all. So what if we think about Gen AI more generally in engineering, chemical engineering? Well, if we apply this idea of autocompletion of code to processes, what we can think of is an autocompletion of chemical flow sheets. So would it be possible to develop Gen AI tools that help you to autocomplete or develop chemical processes? For example, by suggesting the next unit operation, suggesting the design specs of these unit operations, or the operating conditions, and so on. And when we talk about translation, well, is it possible to develop algorithms that help us to develop a P&ID-like diagram from a PFD? So translate an early stage of development to a later stage. Or maybe translate is the wrong word here. Maybe it's rather learning what the engineer is doing. And of course, there's not only the PFD diagram in an input, it's a lot more other documents. Most likely these are multimodalities, right? So we have the diagram information, but we also have text, like process descriptions, requirements, and so on. And last one is quite obvious now. When we can find errors in text, would it be possible to also find errors in diagrams? Okay. So these are the first three applications that I wanted to show you. There's a fourth one that's quite relevant that we also look into in our research group, which is also related to making errors in P&IDs and finding them, especially in the context of safety. So would it be possible to automatically generate HAZOP reports from P&IDs and additional process data? And of course, all of these applications are not meant to replace a human, but rather work together with a human, assist the engineers essentially in their day-to-day work. So if we have this idea of Gen AI or large language models helping us to develop processes, translate from one stage to another, find errors, generate HAZOPs, helping us to do our job. I think one of the main questions is, well, can we just do it with the tools that are out there already? Can we just go to ChatGPT and ask, hey, can you help me to develop my process? Can you please draw a chemical flow sheet for my product, for process developing or producing this product? And I'm not sure if you have tried it. I tried it many times. The answer changes over time, of course, but I give you the general gist of the answer. So in many cases, the models are quite positive, first of all, which is good, right? So I want to hear, hey, I can solve your problem. And what you see is the models also figures out that, well, it needs to generate something beyond text. We're asking for a diagram, so it needs to generate an image in this case. And it takes a bit of time till ChatGPT has generated this image. And if you look at the result, well, what you recognize it's not very helpful, right? So this is very far from being useful or any useful in chemical engineering or process engineering. This has nothing to do with a process flow diagram that I was looking for, that I want to develop. And of course, this is very disappointing, right? So we have these powerful models, ChatGPT. We know they're knowledgeable, they're trained on the whole internet. Still, they're not really useful in our domain if we want to do anything particularly useful. So the question is, how can we overcome this gap between the performance of these general multi-purpose models that are accessible through the internet and our vision of an industrial co-pilot, a Gen AI helping us to do our engineering job? And I think here's worth to step back and look again at what are the key ingredients that made ChatGPT so successful in this text domain for many other tasks. And I think what you recognize, or what I recognized, is, well, it's mostly a combination of the data that was accessible or was made accessible, a meaningful representation of the information in form of, or data in form of text, and then the model architecture, of course, right? So there's a lot of work on the machine learning side developing these transformer architectures that are so powerful. And what we want to figure out is, what do we need to do in process engineering or chemical engineering or organic chemistry, or maintenance maybe, in order to get similar results? And what I want to do today, I want to go through these question marks. But before we move on, I think there's another dimension that we shouldn't forget. And this is the mechanistic knowledge. So we as engineers, we know a lot about the physics, about the chemistry behind our chemical processes. And we use this knowledge in order to make meaningful decisions, in order to develop safe and efficient processes. And we believe we need to integrate this knowledge into the machine learning algorithms, into the smart decision-making algorithms supporting us. And of course, there's like this is a new dimension, because the standard text models, they don't have that. They're mostly or predominantly based on, probabilistic assumptions about the text, basically. So there's a big question mark on this side on the right, where we need to decide, hey, how can we integrate mechanistic knowledge into our models? Or should we at all? Is it sufficient not to do it? Do we need to? So that's the big question mark that we need to fill in our research, basically. So what I want to do today is I want to go through most of these blocks. I don't manage all of them. Give you a bit of idea of what I believe are the first steps that we need to do in order to address these question marks, to fill these gaps. And of course, I want to encourage you to perform research in this area, to help us as a community to develop these models further and make them useful. And the first question mark is a big data one. And here's a simple question that we need to answer. Is our domain, is chemical engineering, actually a big data domain? Because if we don't have any data, well, we can't train any models, and that's going to be very difficult for us to develop, large language models or Gen AI for our domain. And if you read the literature, if you discuss with your colleagues, it's very likely that you find this answer. Our domain is not a true big data domain, because we have limited data. We are not like text or images that you can find on the internet and just train your models on. And this is why we used to develop, we are still developing a lot of hybrid models, physics-informed neural networks, and so on. And we do that as well in our research. I believe in hybrid modeling, physics-informed neural networks. I think there's a lot of value in that. However, what I also believe is there is more data than we use at the moment. So we as engineers, we generate a lot of data in our day-to-day life. We do simulations, for example, in Aspen, for example, in DW Sim, maybe CFD simulations, maybe in Fluent, maybe in other software. We write patterns, we do molecular simulations, we measure properties, we write in lab books, we write emails, we write papers. So there's a lot of different information, data that we generate. So why do people say that we don't have big data or any relevant data in the engineering domain? Well, I think the main issue is not that we don't have any data. I think the issue is that our data is very heterogeneous. It's not findable. It's not machine readable. So it's not easy to, just take the data, give it to machine learning engineer, expect him or her to train a model, give you the results back. We first need to find the data, figure out where it is, make it accessible, make it understandable, make it processable. Think about how we represent it, and then we can start all the machine learning stuff. And if you think about flow sheets in particular, like P&IDs, PFDs, they are also not in the public domain mostly, right? So the real meaningful data is with the companies. And usually it's highly confidential data. So it's not easy for me as a researcher to get access to 10,000 P&IDs from a big chemical company. There's a long process of NDAs, of building infrastructures to share stuff. And then still, it's only individual researchers that get access to this kind of data. There's no public data set for P&IDs yet. And there may never be one, right? Because in our domain, people and companies are very protective of their data. So if you want to do research in this field, it's very difficult to get started because you just have a very severe lack of relevant data. What we did in the past is, in order to get started, we mined a lot of data from books, scientific publications, and patterns. But of course, these data sets they look very different than the actual industry ones, right? So if you compare the P&ID on a patent with a real P&ID of a chemical process, it's completely different, basically. So it's oversimplified. It's only part of a process, probably. Maybe even on purpose be simplified to an extent that is not usable. But if you figure out a way to get this data, or if you're at a company having access to vast amount of P&IDs or PFD data, maybe you have big data available already. I talk to a lot of companies that tell me, like, we have 100,000 P&IDs, no problem. But then still, this data is usually not machine readable yet. Usually these are P&IDs or PFDs that are saved as PDF documents designed for human communication, for engineers. So the challenge is, how can I make the information on the P&ID accessible for a computer? And here development comes in that we have been developing over last 5 years, which is called Digitization Companion, where you can basically read in PDF documents of P&IDs or process flow sheets, and it's connected to a number of machine learning models that we're developing, including object detection, connectivity detection, text detection, table extraction, and so on. And you can run these models in the cloud in order to generate smart P&IDs. So basically, these models are recognizing all the symbols on the P&IDs, their connectivity, and contextualize all of that. And I think I have an example of that. So here we just have an image of a simple P&ID. And here's an example of just the object detection part. If we zoom in, we can also see that a lot of the equipment can be recognized by object detection already. Of course, it's still under development. So we have a few, for example, this valve here is not detected yet. But we are confident that we can do that as well in the future. And this is really necessary if you want to work with P&ID data on the computer. Because you need to know not only the pixels on an image, you need to know what the meaning of of this symbol is. And you need to know how the topology of the process is. And that's what you get in a smart P&ID. Once you have the information in a digital format, we need to think about how to represent it in a way such that a machine learning algorithm can later on process it and learn from it in an efficient way. So if we look at the flow sheet, one way to represent it is a graph structure. So here we can think a bit about basically nodes being the unit operations and the connectivities, or edges being the connectivities or the streams, right? If you go a bit more into detail, you will recognize, well, that's not sufficient. You need to encode more information. Probably you need an ontology. You want to build knowledge graphs, hypergraphs. There's different graph representations you can come up with for a process. There's a different way to represent flow sheets. You can also encode them as strings. This is inspired by SMILE strings for molecules. And this is relevant because it allows you to encode your process information in a format such that you can use standard large language models. So if you want to get a quick success in developing a Gen AI for the engineering domain, it might be helpful to encode your information such that you can just use a model out of the box or fine-tune a text model. If you want to build a big infrastructure for Gen AI in process engineering in the long term, I rather recommend you to change the model such that it fits the data. And then I think the graph annotation or graph representation is more meaningful and more powerful. To give you an example of this graph, here's a part of a P&ID. And here we plot basically a graph representation, a knowledge graph on top of this. And you can see already it's relatively complex graph, given that the P&ID is so simple. And that's because there's a lot of implicit information saved in the P&IDs. And through the graph representation, we try to make that explicit. What you can do as well is you can build abstractions on these graphs, right? So we can sum information together, lump nodes together, and build simplified high-level graph information as well. So that's another advantage. If you have the information in digital format, well, you can apply these operators basically on your data to represent information on different hierarchy levels with different focus for different applications. And you can already connect this graph structure to large language model. So what we did here is we have this P&ID. We encode it as a graph. So this is now in a database called Neo4j. It's a graph database. It's also annotated with additional engineering data, maybe a diameter, an exchange area, and so on, design pressure. And then we can make this P&ID graph accessible to a large language model. And we don't need to retrain this model. We can already use it for asking, for example, simple questions about the P&ID. So here my student asked for like the large language model to describe the process flow from input to output. And what you see is the large language model is actually referring to the individual nodes in the smart data format and just describing the flow sheet. You can also ask for a list of valves here, for example, would give you a list of the valves with their specifications. So here we haven't trained any new model. It's basically large language model out of the box connected to the graph data. So most of the work here is in getting the data ready into an exchangeable graph format or machine readable graph format. But our ultimate goal is to develop new models for our purpose, for the engineering world. And here I don't want to overcomplicate it. So what I want to emphasize is depending on how you encode your information, you need different model types. So if your model, if your information, your data comes in as strings, as text, as sequences, most likely you will end up with some kind of transformer architecture, right? So these are the models behind, or the types of models behind most of the Gen AI large language models that are out here. So ChatGPT is based on some kind of transformer architecture. But if you represent your data as a graph, what you need is you need a machine learning model that is capable of processing graph-like information. And these are usually graph neural networks. So these are architectures that are well known in chemical engineering, mostly in the molecular machine learning world for predicting properties of molecules, for example. But they can also work on flow sheets and flow sheet graphs. And of course, you can also mix and match a bit. So you can have a transformer with a graph encoder. You can have generative adversarial networks, variational autoencoders. You can build diffusion models. There's a lot of variations of Gen AI models, large language models that we can leverage for different applications. Okay, so what I want to do is I want to highlight at least one case study where we trained a simple generative AI model for one of these engineering case studies. And I picked the autocorrection one because I think it's quite nice to understand, quite easy to see what's possible already and what we need to further develop in the future. And as I mentioned, this autocorrection is a bit inspired by tools like Grammarly, and they don't work only with Gen AI. They usually have a combination of rule-based systems and AI systems. And that's what we want to develop as well. And I think that's quite sensible because, well, these rules have a lot of advantages, especially for safety critical stuff, but I come to that. So how do rule-based systems work? Well, what you need to do is you need to implement or define your rules as graph patterns. And what is a rule? Basically, a rule is an error pattern. So potential error you can make in a P&ID with a way how to correct it, with a correction graph. And then what you can do is you can run a rule inference algorithm on the graph that is helping you to find all the erroneous patterns and correcting them. So this is an example. Here we have a P&ID as a graph. And we took a look at one of the parts here. We just have a vessel. And we have a rule implemented which says install a pressure relief valve for all tanks with a design pressure greater than 3 psi. What you see is here's no pressure relief valve. And this is what the algorithm is also recognizing. Hey, there is this graph pattern that is, is basically wrong. We need to apply this rule. And it can automatically add this pressure relief valve. It's not only adding the pressure relief valve, it can also give a message to the user, to the engineer. Hey, I applied rule 23 on this part in a P&ID. Do you confirm? And this running of the rules, it's extremely quick. So we can run rules in hundreds of seconds on large P&IDs. It's extremely reliable as well. So if you implement a rule, you can be sure that it's going to be found and applied. However, there are also a few limitations. It's not easy to implement such rules. So the data models behind the P&IDs are extremely complex, quite detailed, and you need to understand very well what you're doing. And because they're so detailed, the data models, the scope of the rules, it's quite narrow. So you need to define exactly what you mean. Otherwise, you're going to miss it. So it takes a lot of skill to implement these rules. and not to miss it or not to, implement them in the wrong way. So the real vision is, hey, if we maybe implement a few safety critical rules, that would be probably important and good, right? But can we do more? Can we also automatically extract rules or error patterns from existing P&IDs? And this is what we want to do in the future. Basically, leverage the implicit knowledge that is hidden in the existing data. For now, what we did is we did a first step in this direction through a supervised learning algorithm. So here what we did is we have a transformer model, a sequence-based model. So a model that takes text in and text out, kind of. How do we manage this? Well, we represent our data as strings, as these S files. So flow sheets encoded as strings. And the input of the model is a process flow diagram with potential errors. And the output of the model is a corrected PFD. And what we did is we generated a lot of this synthetic data. So we didn't train it on real P&IDs or real PFDs, but we just said, hey, if we have data available, would it work? And if we look at the accuracies, that's relatively high already. So what it says tells us is that in general, machine learning models, these transformer architectures, can also learn from process structures, from process topologies. And not only learn from, but also generate process topologies. So if we give this one as an input to the model, and don't overinterpret here. So this is one of these synthetically generated process flow diagrams. So it's not a real PFD. The potential errors it sees and wants to correct are these two. So what it corrects is basically it says, hey, don't you want to add a temperature sensor here or controller? Does it make sense? Well, to some extent, yes, because I probably want to heat or cool the stream, or probably heat. And then I may want to control the temperature of the outgoing stream through the steam here. The other correction is up here, which suggests to use this valve in order to control the pressure of this vessel. So the question is, are these actually real errors? Is this a meaningful prediction? Is this model any useful? And the answer is, well, we don't know, but at the current stage, it's not useful yet. So why can't we answer whether this is a meaningful prediction or not? It's difficult because we don't know the context. And the point is that the model doesn't know the context either because there exists no context at the moment. So all the model sees is really the topology information here. So it doesn't know what is produced, why. It doesn't know anything about the process except the topology information, basically the information you can see on the drawing here. And without this context, it's very difficult to evaluate whether something is an error or not, or done on purpose, and how to correct it. We would need it as engineers, and the model needs it also. So this is one of the key limitations of the current model, and something we need to address in future research. Like, how can we give the model more context in order to make meaningful predictions? But on the bright side, what we see is these models in general can learn from the process topology and can generate it as well. And they can pick up these error patterns in the data. So what I showed you are these individual applications here. And we have trained individual models for all of these applications. But I think what is important to recognize is that there's a lot of synergies. And you can see that in ChatGPT as well. So ChatGPT as a large language model, it's not particularly successful because it's very good at one specific task, like writing a poem for the birthday of my mom. It might be quite good at that, But that's not why you use ChatGPT, probably. You use it for completely different tasks. And it turns out to be good at many different tasks because it has seen so much diverse data. And it somehow leverages synergies between different tasks, even different languages. And I think that's what we need in our domain as well. We don't aim to develop individual models for autocorrection, HAZOP, and so on. What we aim for is to leverage some of the underlying knowledge that all of these different tasks have in common. So basically leverage the synergies. So have more foundation kind of models for our industry. And there's a second idea that I believe is quite relevant. That is the idea of multi-agent systems and multi-model information and tools. So I believe there will be not one model doing the whole process development in one step, right? So this is unreasonable to expect. I believe it will be individual models communicating with one another and also using our tools and data and databases. So when you develop a chemical process, you're using databases to get properties, simulation software to estimate how the distillation column might behave. Maybe you look into a book in order to get a heuristic in order to design the sequence of a distillation column. Or maybe you just remember it from your studies. We need to make all of this information explicitly accessible for the large language models as well. And we can do that through tools. And before I finish, I want to just give you one example to give you a bit of an idea of how it looks like or works, this interaction of large language models and tools. Here we have an example of a chemical database with properties. And what we did here is a very simple study where we ask, hey, large language model, can you ask a SQL database, a relational database, for the properties of a particular substance? And we made the large language model generate the query code as a string, and we just pass that on to database. And turns out this works quite well. And we're not the first to do that. So this is already established knowledge. You don't need to retrain your models. There's frameworks helping you to do this in an efficient way. But setting up these pipelines can basically help you to connect large language models with structured information. And you can also use the same principle of basically large language model being able to output structured text also for generating models. So here we trained a large language model to generate Modelica code in order to simulate dynamic reactors. So there's a lot of potential in connecting large language models to these different tools and databases, but also training new models on our data. And this you can only do, and we only did in collaboration together with industry. So I want to thank my collaborators. I think these collaborations are really key to successful innovation in this area. And I'd like to conclude. I think the digital engineering data is really key for future AI applications. The good news is Gen AI can learn from and generate flow sheets. Collaboration is key, otherwise it's not going to work in this area. And I think there's a big potential of Gen AI and large language models to change the way we design processes. And I'm interested to hear about your opinion, and I'd like to thank you very much for your attention.
Fantastic. Well, Artur, fantastic presentation. Great overview, not only of your specific contributions, but kind of some of the, the trends that are going on within chemical engineering. Just for those, we've got about 8 people who have already responded to the poll. I'd love to get your thoughts just as we head into the question and answer. We have a few questions in there. First question is, how are you currently using or planning to use large language models in chemical engineering? And so in terms of process systems engineering, there might be process optimization and control, research and literature review, data analysis and predictive modeling, automating documentation and reporting, or I haven't explored LLMs yet. Second question, what concerns you most about using LLMs in chemical engineering applications? One, accuracy and hallucinations and responses, data privacy and security risks, lack of interpretability and explainability, computational costs and infrastructure needs, or I have no major concerns. We also have a third question there. How quickly